Good afternoon, participants. A very warm welcome to our next speaker of session 2, Dr. Abhishek Midya. Welcome, sir.
Thank you, Dr. Mal.
So now I would like to give a brief about Dr. Abhishek Midya. He is a postdoctoral researcher in Memorial Sloan Kettering Cancer Center, USA. And the title of today's talk will be Are Radiomic Features Reproducible with the Variation of Imaging Parameters? So Dr. Abhishek Midya did his PhD from Indian Institute of Technology, Kharagpur in 2013 on image and video processing. After completion of PhD, he joined National Institute of Technology, Silchar in 2013, where he worked until 2016. In 2016, he joined Memorial Sloan Kettering Cancer Center, New York, as a postdoctoral research fellow. His research interest is automatic detection, diagnosis, and prognosis of different cancers, treatment, stratification, etc. So, without further ado, I would like to hand over the session to Dr. Abhishek Midya for his talk.
Thank you, Dr. Mal. Should I start now?
Yes, sir, definitely.
Good afternoon, everybody. I'm Abhishek Mehta. Today I will give my talk on are radiomic feature reproducible with variation of the imaging parameters. So before going into in detail, I first give some idea of what is radiomic features and what does it mean by reproducibility and how it varies with different imaging setup. Before going to my talk, I first whether I before just I have a question. Whether are you able to see my screen?
Yes, we can see your screen very clearly.
Before going to in details, just first give you a brief idea about our institute. Currently, I am a postdoctoral researcher at Memorial Sloan Kettering Institute for Cancer Research, and it has two parts. One is Memorial Hospital, another is the Sloan Kettering Institute. In in Sloan Kettering Institute is mostly postdoc-driven institute, where we don't have hardly have any undergraduate student and few masters and PhD student, and mostly around 3,500 postdocs. This is one of the one of the buildings of our institute, and there are several another 3-4 buildings. And we generally don't go outside for data collection. All of our data is supplied by our own hospital, Memorial Hospital. This is one of the world's best hospital in cancer care. So whatever we found in our research, again we do patented and all those things, and we use for our new treatment planning. So it's a unique concept, and hospital is backup supported by a huge research team. So in last few years, we have found that computerized method in treatment planning have been evolved very rapidly. There are several reasons behind this. One of the major reason is that insufficient number of radiologists or pathologists in developing countries. There, although in particularly countries like India or Africa, there is no sufficient number of radiologists or pathologists. So in those countries, the computerized methods are very helpful. Then another interesting reason is the speed of diagnosis. Say if a radiologist have to go and see a scans of a patient, then it takes nearly 4 or 5 minutes. Then whether a computer-based methods can take a decision on within a minute. So when large-scale populations are there, then computerized methods are very helpful to get very early results. Third one is the improvement of performance. Although radiologists are good at their task, but it is found if a radiologist or pathologist are aided by any computer-based system, then his performance is improved by at least 10%. So any computer-based method will help you as a second reader. And there are in many times it is found that there are some information are hidden within a image or within any pathological slides which we cannot see in a human eye. But there are some information, these information can be extracted and may be useful for detection or diagnosis or treatment planning for a patient. So to extract this information or to explore this information, we nowadays computerized methods in medical treatment planning becomes very much important aspect. Nowadays, in 10 or 20 years back, we call it a radiographic images. But these images are not only as just a picture; they are a data. In last 20 years, if you see that huge improvement of imaging resolution has occurred. It is a revolution. Even our smartphone is having 20 megapixel camera. So it is not in the smartphone industry, all healthcare industry, in healthcare industry also imaging has been improved by lot. So earlier many tissues were not visible, but with the ultra high scanning system, many tissues and many other organs are nowadays visible in CT or MRI or any other kind of image modalities. And with this very ultra high resolution image, there are two types of image analysis becomes very popular. One is qualitative image analysis. In qualitative image analysis means here radiologist see an image and he assess based on his perception only. Where is tumor and what is the size of the tumor or how tumor is differentiated from the background or any of the background organ. But it has some demerits too. One of the demerits is a human error. A radiologist may have done some mistake. And another is that inter-observer variability. What inter-observer variability is an inter-observer variability means we observe even at the best level hospital that there is a variation between the observation of two radiologists. And it may be sometime based on their experience, sometime based on their fatigue level. So this should be avoided in a treatment planning or in a diagnosis. It shouldn't be affected on based on the quality of the radiologist. So in last 10 years or 20 years, you can see that quantitative image analysis becomes more and more popular. In quantitative image analysis, what is the radiologist observation? We try to quantify those observations by extracting some information. Say earlier radiologists measure the size of the tumor. Now we will try to make it an automatic process to measure the size of the tumor or the location of the tumor. And for the analysis for analysis of an image, nowadays we extract a high dimensional of data from individual images. And this high dimensional data is called radiomics. And if you go to and this use of this radiomics becomes very much popular in medical image analysis. And radiomics is mostly called to the radiological images. If you have pathological images, this we call it pathomics. But basic idea is we extract a huge amount of information automatically by computerized method to detect or diagnosis or find the prognostication of a disease. But problem is that if you go in last 10 years, a huge number of features have been proposed. I can say in breast cancer, if you survey the manuscript, you will find at least 5 to 10,000 paper on breast cancer classifications. But if you say really practically useful tool is very limited, within 50 or maybe 100, not more than that. And what is the reason although we have developed so many features, and in manuscript, people have reported almost they have got 100% accuracy. But still there is some gap where we don't get much commercially available tool which can really be helpful for the doctors to provide better patient care, and for patient term they are also getting best treatment at the earliest by early detection or the best detection. So there are some gap between this research on the development of new imaging features and the production level or commercial software. Actually, what is found that most of the features developed in our laboratory, they are not found reproducible enough. Or when we are trying to validate with some external data, this software failed. This texture, these imaging features, quantitative imaging features doesn't able to provide a sufficient performance. So we have to check whether imaging feature is a good or the reason behind it. So what is the problem? One is lack or improper. Many of the times, when people publish paper, they don't did proper validation. And so what happens? So they don't take external data; they take a limited set of data, and sometimes they do the validation method or experiment on their method very wrongly, and which leads to they give them a very high result. So in many of the problems we may find that in literature people have got almost 100% accuracy, not less than 95%. But when we apply these methods for a practical use, we found that the accuracy dropped to something around 70%, and which is not a reasonable to use for a medical practice, and after all, as it leads to a life of a person. Another is that sometimes it is found that people have a high dimensionality of features and very small amount of data. That means they have very small, say somebody is developed a method for classifying a cancer patient whether it is benign or malignant. So he have only 20 patients and he has extracted, say, somehow 1,000 features, and which is naturally gives them an overfitted result. And another aspect we are recently studying, that is reproducibility of the features. How our features are varying over different imaging setup. We have developed some feature. Now, when we change our X-ray machine or CT machine, how this feature varies over different manufacturer or different image acquisition or reconstruction parameters. That thing must be studied. So these things are generally not done by the researchers. But these things are very essential to make somebody's research to a commercial product. Because otherwise, when you do research, we publish our paper, we just get some good result and we are happy. But to make our research into a commercial product, we must check the reproducibility of the features, and we have to do a very good validation. of our texture, our features. There are, if you see, there are two images. These two images, we can visually see there are some differences are there. If it is asked to any layperson like me, I can say that these images are more contrast, right side images with more contrast, whereas left side image is having less contrast. In right side image, this is actually this is a image of a tumor. Sorry, this is an image of a liver, and all these black spots are liver tumors. So if it is asked to me, I can say these tumors are very easily distinguishable from the background, whereas these tumors are very difficult to see. Her boundary is little bit blurred. So even these tumors is not properly visible in that image. But if you take these images to a radiologist, he will say there is no difference between these two images. These are a liver and the tumors of a same patient, and these two scans are from one particular person. So in our bare eyes, we can see although there are significant difference, but radiologists can identify that these two scans of a particular patient. So when we developed about machine learning or any image processing methods, one of the reason of failure like this, and ideally it is true, one of the right side scans are done at our institute and left side scan was done some other institute. And these two scans were done within 7 days. And the patients were not taking any medicines and they were scanned in a same manufacturer's machine. So same person, same manufacturer machines, still there are some difference in the appearance of organ as well as tumor in situ. So there are something, and as these appearances are different, so very often if we develop some imaging feature based extracted from these images, so our results may vary. So it is so we have to find it out the result behind this variation of appearance. One of the things we found, this machine dependency is a reason behind this kind of variation. And even for the same manufacturers, two different models, we found that there is a variation in image. Then we studied the acquisition parameter or CT dose. CT dose means amount of CT beam exerted on a patient. Generally during CT scans, we push some contrast enhanced. If it is contrast enhanced CT, we generally fed some contrast amount to the patients. Then after some time, we exerted CT dose on the patients. Then later on, radiologist and we collected the data via different sensors, and later on, radiologist reconstruct that images. And we found the volume of the contrast injected is also responsible. And during the reconstruction of the CT image, the radiologist set some parameters. So based on the parameters also, these appearance may vary. So we consider only these four things, but there may be some other things also, because it is not possible to study all possible reasons at a time. So first we did a phantom study, because one thing is that one of the variation reason is the acquisition parameter. Acquisition parameter means we have to put a CT beam on a particular patient in different dose, which is not safe for a patient. So first we did on phantom study. Then we extend our study on actual human patients. In phantom study, we first try to check variation due to acquisition and reconstruction parameter. In acquisition parameter means when we vary the CT beam, how our image quality changes, and reconstruction means after when we reconstruct the CT, how the CT appearances changes with and any texture feature extracted from the CT scans, how they are varied over the reconstruction. So for this purpose, we have chosen two type of phantom. One is uniform water phantom, another is anthropomorphic phantom. This is a CT machine and this is uniform water phantom. Uniform water phantom means it is a plastic, circular shaped plastic box is filled with some water-like content, not exactly water, and we scan this object. And another is anthropomorphic phantom. This is looks like a human body, and within this plastic body, we put some plastic things which is very similar to our human organ tissue material. These two products are a proprietary of GE Healthcare. And so what is the actual material, all those things, it is beyond our knowledge. These two phantoms are generally used by GE to adjust their machine. Then we extend our study with one human patient for whom we vary only the reconstruction parameters, because for human patient we cannot vary the acquisition parameter because we cannot say multiple amount of dose in different time, and it is not safe for his body. So we will never get approval for this kind of study. So for human, so we have incorporated one human patient. For phantom study, we vary the check the results with via variation of acquisition as well as reconstruction parameter. But for the human patient, we did the study only on the reconstruction parameters. Now we extracted GLCM, angle cooccurrence matrix 1, angle cooccurrence matrix 2, intensity based histogram, local binary pattern, RLM, and fractal dimension. These well-known texture features from the CT scans. And now we try to find out how these texture features or imaging features are varied over the variation of the acquisition as well as reconstruction parameter. So ASIR is one of the reconstruction parameter which radiologists often varied. ASIR means adaptive statistical iterative reconstruction method. And this is also a proprietary of GE's Healthcare. So we don't know what is the formula of the ASIR or how ASIR works in detail. But what we found that with increasing ASIR, image become blurred. So if you see, this is for ASIR, left column is the ASIR 0, then ASIR 30, ASIR 60, and ASIR 100. We can vary ASIR from 0 to 100%. So as we move from 0 to 100% for all type of images, whether it is UWP, maybe anthropomorphic phantom, or maybe human scans, for all kind of images, the image becomes more blurred. And more surprisingly, what we observe from when a radiologist doing reconstruction, he has two radiologists set two different ASIR level for one particular scan. So one radiologist said, I can see better that particular image on ASIR 60, and another radiologist said, no, I can see better at ASIR 30. And also for different organ, different ASIR level may be beneficial. Now, when you extract different features like GLCM or ACM, we found with the increasing of the ASIR, some feature value is constantly increasing, whether some feature value is constantly decreasing. Sorry. So what we observe, the features which describe the homogeneity, these features values are constantly increasing with the increase of ASIR, but the feature which represent heterogeneity or more deviation in the pixel values, their values are decreasing. But if you see in different feature value over the variation of the ASR, you might observe that they have a monotonically increasing. It is not they are increasing abruptly. So there is some pattern to for their increment. But this is our qualitative observation. So we want to try to find out a quantitative observation. So we use a parameter called concordance correlation index. Concordance correlation index give you how two features are very much correlated from these two scales. So ideal value, this is the formula of the concordance correlation index. And concordance correlation coefficient ideal value is 1 if both the scans are same. So what basically do, the capital X is the, say you have 100 images and you have extracted one feature. So X is the, so you have 100 patients and you have scanned them twice with two different machines. So X means that you have extracted one feature. So X means that one feature for all 100 patients at the first scan, and again the same feature for the second scan is Y. And this formula gives you the how the feature extracted from the scan at the first scan and the second scan are correlated. If concordance correlation index is more than 0.95, that means it is excellent. If it is more than 9, it is good. It is more than 80% or more than 0.8 means it is still not very good, but still not bad. But beyond that, we can say this features is not at all correlated over that variation. Now, for the human scan, what we did, we have only one scanning parameter and we reconstructed the image with different reconstruction value or ASI. So if you see, and we plot their CCC value with this color code. The color towards green means it is very high, almost 1, and towards black means it is almost not at all correlated features. So what we did, we take individual, so here along the x-axis, it is 10, 20, 40, 50, 60, 70. These are the values of the ASI. And we have considered altogether around 254 features, which include angle co-occurrence matrix 1, angle co-occurrence matrix 2, fractal dimension, 128 LBB features, 5 intensity histogram based features, then few run length matrix, and then 19 GLCM features. And along x-axis, we have shown that ASIR values. So, and our baseline is the ASIR 10%. So we compared ASIR 10% with ASIR 10% for each feature, and their values is convert. Now, if I am to show some numeric value, it will be very difficult to see. So I put there in a color heat map so that from color code, you can see that which features we can easily identify which features are reproducible and which features are not. The features which are, say, for ACM1, for always some features in this region are always stand in the green region. So although we are varying ASI, this feature value doesn't change much. It is almost in the very highly reproducible zone. Whereas some feature in the fractal dimension, in the initial increase of ASI, it is good, but as ASI is increasing, it turns towards the dark region. And some feature of the LBP is not at all reproducible, that it is from the beginning also it gives you some high, low value of the CCC. So if I want to develop a system for some detection, we have to consider only those features which are non-variant to ASIR. Then we can see, say, if you select some ASM feature, ACM2 features, LBP, some of these features from this region, and some features from this region and develop a system, then we can say that these features are not at all variable with variation of the ASI. So if we build a system based on these features, we can claim that our system doesn't suffer from ASI variation. Now this is for the anthropomorphic phantom. That means that human phantom. And here we are able to vary the CT dose. This NI12, NI14, NI16, these are the CT dose variation. And along the y-axis, the same number of features that SCM1, SCM2, fractal dimension, local binary pattern, as well as intensity histogram, RLM, GL7, and all those things are there. Now here you can see first it is basically repetition of these things. So here within NI12 up to this is basically when we accuse the image or take the CT scans with NI12 and reconstruction variation from ASI at 0 to 100%. Again, from our image acquisition is NI14 and it reconstructed with from 10 to 100%. We vary the reconstruction parameter. Again, we take the image with noise index 16 and we again varied from 10 to 100%. And same thing for NI18 and NI20. Now, from these scans, we can say if we take any features from this region, which is almost black over almost green over the variation of NI as well as over the variation of the ASI. These regions are totally in the green region. So if we take these features, we can say our features are adaptive to acquisition parameter like CT dose as well as reconstruction parameter of the ASI. But if you do not study this thing properly, what will happen in our small data set? Say you may find that one of the features from this region, you may find that it was give you very good result, but when you make an external validation, you may find that your method fail tremendously badly. So we have to do this kind of analysis before taking our imaging features to a final product. And this is the same result for the uniform water body phantom. Actually, this scans was done in another different machine. Both are GE's machine, but these machines we have an option not changing the noise index. Here it was tube current. It is 50 milliampere, 100 milliampere, 200 milliampere, and we varied it from 50 milliampere to 500 milliampere. Basically, noise index and tube current are same parameter. Two of the GE's machine have two different buttons, and basically they control the amount of CT dose exerted on a patient. So for this anthropomorphic phantom, you may see that none of the fractal dimension feature were stable over the variation of the acquisition parameter. Only few ACM parameters, although lesser than this, and some of the was say one feature from this row. Actually, each row signifies one features, and here corresponding NI or ASI values. So if you take one feature from these features are very much stable. So if I take only the features from these regions, only from the green regions, purposefully select the feature from this region, then we can say our method or these features, or if we develop any CAD tool, then we can say our CAD tool is not variable. We can not variable with variation of the ASI or tube current or noise index. And this you may find the details about all images and all methods and study protocol in our recent publication. Then we did a liver study. Then we have taken 37 patients who are scanned within 2 weeks, but they are not undergo of any medications, and they didn't suffering from any major illness rather than their cancer, liver tumor. And we take, when we have extracted these 255 imaging features from first scan and from second scan, and then we compare how they are different. And during this study, we found two interesting observations. Actually, those who are doing the scans, they were not all the laboratory assistant and technical stuff. They were not, in general, when we do an experimentation, these staffs are unaware of what is our objective. So they were not aware of that scan. So all patients as well as scanning related technicians and some of the radiologists don't know about that we are doing a study. But so there we have observed a funny thing that a person is given a contrast amount of say 10 ml, and another person gives the contrast dose of 15 ml, and we found there is a variation of up to 50% variation of the contrast dose injected, and which affect the result much. So although I have told that all these patients are scanned within 2 weeks without any medications, and this scanning was done randomly 2 GE machines. So a subset of the patients were scanned in same machines, and subset of the patients patients, we found that there are two scans is done in two different machines. But both the machines are made by GE, but with different manufacturers, different model. And we extracted the same features: GLCM, ACM1, ACM2, intensity-based histogram, local binary pattern, RLM, and fractal dimension. And we measured the reproducibility of these features extracted from liver parenchyma, that means liver region, as well as we have the segmented liver, segmented tumor. So we extracted the same feature and we extracted the same feature from the tumor region, and we found the reproducibility. So first we did this thing for liver. In liver, if we see the contrast injection rate is below, difference in contrast injection rate is below 15%, then we found that 60 features were having CCC more than 0.9. Around 110 features we found CCC more than 0.85. And nearly 145 patients, 140 features which are CCC more than 8. Now, when contrast injection change in contrast injection rate means 15%, means these patients, say contrast injection rate varied between two scans below 15%. Say if during first scan they have given 100 ml, in the second scan their contrast injection rate in between something 8.5 to 11.5. And then second set of people, those who were scanned twice, but their contrast injection rate varied within 20%. So there, if you consider this group, then we found our CCC value dropped suddenly. That only CCC greater than 0.9 is only for around 20 patients. CCC greater than 0.85 is something around 80 patients, and CCC greater than 0.8, this comes 120 patients. So now if you go towards right, that means change in contrast injection rate increases. So as we move from lower change in contrast injection rate to higher change in contrast injection rate for the liver region, we found that reproducibility of the imaging features which we have considered, they are not becoming reproducible enough. So we have to somehow control the contrast injection rate. If we cannot make constant contrast injection rate, then our system may not give you the accurate result. Then we have just sorry, this will be actually these images are for contrast injection rate for the liver for the tumor region. So here my title is wrong. So this is for the contrast injection rate for the liver region, and this is for the contrast injection rate for the same curve for the liver region. And these two curves are, the radiologists often change the pixel resolution, or sometimes different CT imaging machines have different pixel settings. So if we change or sometimes we can change our pixel resolution, that means how much amount of distance in our body is represented by one pixel. Although it is in the micrometer range, but if we change that variable, we may found that number of reproducible features have been changed. This is very quite often, because when we use different feature extraction modality, most of the time we use a window-based method. And this window-based method is based on the pixel. So if we put a window and pixel resolution varies, that means we are considering different amount of length in our body. So that is very common, and it is very obvious thing. But still we found that sometimes it is the capability of the CT scans, and sometimes radiologists change their pixel resolution to see better. And here is also a funny thing, that a same image of same patient, two radiologists set two different pixel resolutions. And if you see, if between the two scan pixel resolution changes as well, then we also find the number of the reproducible features decreases. So here, if you found that when pixel resolution is below 5%, number of reproducible feature is 10, and as it moves towards more variation in the pixel resolution, when it is less than, when we consider between 12 to 15%, then probably there is no feature is well reproducible. And you will find details about these results in our publication. And then finally, we study the machine dependency. Among these patients, how many of them are scanned in one machine, and how many are scanned on different machines? And based on this, we have made a study. So we found the CCC more than 0.9. Out of this, same scanner is most of them. When we have use the different scanner, then number of feature less than greater than CC 0.9 is very less. And when we have a mix, naturally we have got something in between. So I repeat, when we have used the same scanner for scan 1 and scan 2, we found more number of reproducible features. When both the scans are two different scanner, then we have found that less number of the features are reproducible. And when we have a mixed population, then naturally it is we got something in between these two. And followed, this study was followed for the liver region, last study. So if you have to develop any tool for detection or diagnosing disease on the liver disease or liver tumor, if you extract texture feature or imaging feature from liver region, so you have to select any features which are comes within this 0.9, So if you select any feature from this, then you can say that our features are very much reproducible up change of pixel of 5%. If you select any features from this set, then you can say our these features are very good. It can tolerate up to pixel resolution of change in pixel resolution of 8%. Or similarly, you can say in terms of the contrast injection rate also, that if you select any feature from this region, you can say that our method can, you can select any feature from this set, you can say our CAD tool or our tool can be very tolerant for up to 20% of the contrast injection rate for liver. Same thing, if you want to develop a system based on the tumor, then you have to select your feature from this region. So you have to, so it may lead to that your some features which is very reproducible for over the pixel variation for the liver region, the same feature may not be good for the tumor. So before forming a final CAD tool or production level item, you have to analyze those things, that which features from the liver region, or if you take extracted imaging feature from the tumor region, which are the feature from the tumor region are reproducible, and in what condition, what are the items or what are the condition you validate. Whether it may be machine, maybe pixel resolution, or maybe any other things. Because we have studied only these things, there may be something more. Now we have our previous study was on liver. Then we try to extend our study towards other organ. We studied this extend this study for the pancreas cancer. So these 37 patients who have liver cancer, some of them were having both liver as well as pancreas tumor too. So we have here we try to see the variation over the segmentation and the other scanning parameters. So for this, the same set of patients, 37 patients, we consider those who are scanned within 2 weeks without any medication, they are not in much seriously ill. Oh, one point I forgot to mention, you may think that within 2 weeks, this tumor or pancreas may disappear. But biologically, if a patient doesn't take any chemotherapy or any other radiation therapy or doesn't take any medication, the appearance of the CT scan doesn't change much in 2 weeks. And that's why we consider we scanned these 2 patients within 2 weeks. So all these patients was not either any medication, they didn't get given any chemotherapy, neither any radiation therapy. So which changes their appearance in the CT scans. One of the person have questioned that kindly explain reproducible liver tumor graph once again, explain the excessive and corresponding values. Okay. This is a contrast injection rate. We have an individual patient was scanned twice. So first time they have given one amount of contrast injection, and as these persons are not technicians or may not be same and they are not unaware of the study, so in the second time they might have given different amount of contrast. So say assume that one person was given first time 10 ml contrast injection and second time he is given 11 ml. So the change in variation is that amount of contrast injection rate is 1%. So here along the x-axis we subgroup the patient when contrast injection rate is within 15%, then within 20%, then within 25%, then within 30%. And along y-axis we plot number of features found reproducible for these groups. Now within 15%, if you say J, when contrast injection rate within 15%, the number of which then all these three blue, orange and green lines represent number of for these less than 15%. So this blue color indicates the number of features having CCC more than 0.9, number of features having CCC more than 0.85, and number of features having CCC more than 0.8. So this thing will give you the number of features with different CCC level with the variation of the injection rate within 15%. Now if you consider extend the change in contrast injection rate from 15% to 20%, that means say in first instant it is given 10 millimeter and second instant he has given 12 millimeter. So you have to consider that subset of the patients, and then we found that as contrast injection rate increases, change in contrast injection rate increases, naturally the images are visibly, appearance of the images has been changed, so naturally number of reproducible features decreases. Now here we want to study the effect of the segmentation. So many of the times either we do automatic segmentation, or many times many of the systems we build up or based on when we evaluate our results. Initial level we do research, we do manual segmentation. A manual contour of any organ is drawn by some radiologist or sometimes some technical assistant, and we extract texture feature from the manual segmented objects. And later on we try to get an automatic segmentation. So we try to find it out what is the effect on the segmentation and other scanning parameters. So we have segmented our pancreas as well as pancreatic tumor by two expert radiologists who are in practice more than 10 years. And we extracted to make the consistency, we have extracted the same set of imaging features. Because if you want to develop some system, we have to find out the most common subset of the features. So we extracted the same set of features. Now we have done 3 experiments. Now experiment 1, we try to find out the how the segmentation in between two radiologists. S1 means scan 1, R1, R2 means radiologist 1 and radiologist 2. That means radiologist 1 segmented all the first scan and radiologist 2 segmented all the first scan. Then we extracted the imaging features from those scans, and finally we calculate the reproducibility of the features. Then S2, R1, R2 means radiologist 2 segmented the first scan, both pancreas as well as the tumor, and he again segmented the scan 2, and then we found that we extracted the texture features and we found how correlated these features are. Basically, we have 37 patients, 2 time point. So we have 74 scans. These 74 scans are segmented first by 2 radiologists. And then this scans is segmented by 2 radiologists, 2 set of radiologists. Then we try to find out the effect on the reproducibility of these well-known imaging features on their segmentation. So first scan 1 was segmented by radiologist 1 and 2 both, and again scan 2 was segmented by both radiologist 1 and 2, and we tried to find out how much features they found reproducible from. In experiment 2, we have do a different set of things. Then when radiologist 1 segmented both scans, scan 1 and scan 2, and we found whether we extracted texture feature from this segmented region, and we tried to find it out whether they are reproducible. Same thing is repeated by radiologist 2. Radiologist 2 segmented scan 1 and scan 2, and then we try to find out the reproducibility. It will give you the whether there are any variation of the radiologist observation, whether how radiologist can see the two scan, because there are some difference between two scans and how two radiologists act for these two scans. And first one give you that for a particular scan how two radiologists acted. And in the third experiment, we have totally make a random ordering. So what we did, reader 1 or radiologist 1 see the scan 1 and reader 2 see the scan 1. And in the second thing we did, the reader 1 see scan 1 and reader 2 see scan 2, and we find the CCC for these two. I'm trying to repeat it one more time, that we have 74 scans, 37 at one time instant and 37 at the second instant, and we have two radiologists. So what we did in first experiment, it has been having two parts. So first 37 scan were read by radiologist 1, and they have marked the boundary of pancreas and tumors. We have extracted from their segmented region, and we have extracted these imaging features from this is one set of features. And again, second radiologist see the scan 1. We extracted the imaging features, quantitative imaging features from this scan 2, and now we compare how the imaging features varied over this set. Now, same thing we have done for the scan 2. That means scan 2 first read by radiologist 1, and he has drawn his contour. And again, scan 2 is read by the radiologist 2. He has drawn his contour, and we extracted the imaging feature from those areas, and we tried to find out how much reproducible the imaging features based on this segmentation. And then we make a changes that radiologist 1 see in scan 1 and scan 2. So what is radiologist 1's observation variation between two scans? Again, radiologist 2's observation between two scans, and third one is totally randomized, that reader 1 see scan 1 and reader 2 see scan 2, because this is quite often happen in a radiology center. That when you do scan, one time scanning may be seen by one radiologist and your second scan may be seen by another radiologist, and they are writing reports. So reader 1 on scan 2 versus reader 2 on scan 1, and they are reproducible, and check their reproducibility. We can show you some of the segmentation variation of the two radiologists. This is the pancreas region. One of the radiologists marked is this is as a pancreas, and another radiologist marked this region. And here dice coefficient, that means which gives us how two radiologists' opinion are similar, is very good, 0.94. But in this pancreas tumor region, their dice coefficient between two radiologists are very poor. For this case, interagreement between two radiologists were very poor. With this radiologist marked this area as tumor, whether the second radiologist marked this area as tumor. Naturally, when two radiologists mark two different regions as tumor, and when you extracted the tumor, any imaging features from these tumors, your imaging features varied by a lot. And we have an average dice coefficient for the pancreas parenchyma. It is 0.85. That is, R1 means radiologist 1, R2 means radiologist 2. So when we have when we have found the dice coefficient for the pancreas segmentation, then dice coefficient is 0.85. That is very good. 1 is ideally, but hardly will get 1. This is very good. But the pancreas tumor region, we didn't get very good dice coefficient. So naturally, there is a chance if you extract imaging features from this region, probability of their reproducibility may be less. So let's see what we have got. So as we extracted the same set of CCC, so for when we see that scan 1 by radiologist 1 and radiologist 2 and their reproducibility, we found number of features reproducible is 0.5, very reproducible. I mean reproducible greater than 0.9 is 58, greater than 0.85 is 99, and greater than 0.8 is around 140. Now, when scanned two of the same set of patients seen by the radiologist and we extracted the features from their segmented area, we found there is a slight drop of number of reproducibility. Yes, there is a drop. And that drop causing from the imaging setup, because here same set of radiologists draws the contour. So when we see that there are change in some reproducibility, there are some change in number of features reproducible. So we can conclude that this thing occurred due to the appearance of the images, and that is mostly from the imaging setup. Now, when radiologist 1 sees scan 1 and scan 2, and radiologist 2 sees scan 1 and scan 2, their performance for two different scans are almost very similar. So when there are two expert radiologists, if one radiologist sees both the scans and another radiologist sees your both scans, you extracted the imaging feature from these two set of CT scans, you might find the almost similar number or same set of the features from reproduce. And here we, although the number of set of reproducibility is less, so probably there might be something say radiologist sees, when radiologist sees S1 and S2 and draws the boundary and we are extracted imaging features from that area, so number of reproducible features suddenly dropped. So that means there are something difference are there in between scan 1 and scan 2 due to their imaging setup. And this is the cases when radiologist 1 sees scan 2 and radiologist 2 sees scan 1, and this is from the third experiment. So there also the results are not so much varying. Yes, definitely it is less number of features found reproducible from the first experiment, but still there are some features. So we can say the radiologist observation doesn't have much effect, rather imaging setup has some effect. And here is a curve we put. So along the x-axis we found different CCC, and along the y-axis we plot all those features. So if you find for the experiment, the blue curve means experiment 1 having most number of the features in the CCC. So you can get from, if you have to select one feature, then you have to select all. To develop a system for the pancreas, you have to select all features from which are following at the right side of the curve, and you have to discard the features which are left side of the curve. Here basically it gives you the number of features having more than 0.9 is 58, but here you can see what is their exact value. So it is another representation of that first plot only. Now we go with, and one thing is very important, that the inter-observer variability or the inter-observer agreement between two radiologist observation is very close. They are 0.84. That means it is very good. Whereas when we want to take the reproducibility for the pancreas tumor, the same experiment for experiment 1, in earlier case, we have got 58 and 48 number of features which are very reproducible. Here it comes down 1 and 17. That means for the pancreas tumor, detecting a pancreas tumor is very difficult for the, not only for the system, for the radiologist too. because this is one scan one is seized by radiologist 1 and 2, and this is scan 2 seen by radiologist 1 and 2, and we have already shown that there is very less inter-observer agreement between two scans. So for the pancreas tumor, we found that number of reproducible features are very less. So if you have to if you have to sell some, or you have to design one CAD tool, automated tool for any pancreas tumor disease detection, or any pancreas detection, or any kind of liver tumor detection, or any information extract you need extraction from the CT scan for pancreas or liver. So what you have to do for pancreas tumor, you have to take features from this set, and from liver tumor you have to check and take images which are highly reproducible from that set. And from these two, we can say from the pancreas region there is hardly any effect on segmentation. Based on the radiologist observation, there are hardly any difference. So a segmentation doesn't give you much difference. But in pancreas tumor, the segmentation performance is poor. Naturally, the performance is deteriorated much. One is that we need a standardization of the image acquisition and reconstruction parameter. First of the things so what is the solution to overcome this? First thing what we have to do, we have to do very good image acquisition as well as reconstruction parameter standardization. So during the image acquisition, we have to set up and we have to vary any acquisition and reconstruction parameter very precisely. Say for the contrast injection rate, you have to set it constant. The technician must be very cautious to measure the contrast injection rate, and or CT dose rate. Although it is depends on the radiologist, but still we try to find it out some method to standardize those. And we can do some of the reconstruction techniques mainly required for the standardization. Also the standardization of this clinical protocol, that number of the contrast injection rate, or when we set the acquisition parameter, this is very difficult. Because once we have observed in one of our problem itself, we found that one set of feature found very associated with some disease, but this set of images was not associated with that disease. And these those two set of images are from two different centers. Then we found their scanning protocol is totally different. So standardization of a clinical protocol is very difficult issue, because radiologists throughout the world should agree, and then only we can make any changes on this scanning. So what we engineers can do, we can do a feature normalization method. Engineers or statistician can do a feature normalization. So we will have all information, number of contrast dose in a given, number of what is the CT dose, what is your reconstruction parameter, and what was the pixel size. We can extract those images from in your CT image header. Generally, all these information are present. So we will have this information. Now, based on this information, we can normalize the CT scans. The feature value extracted from a CT scan, we can normalize this thing to eliminate that effect of any variation over the acquisition and reconstruction. And currently we are working on that. But there are several problems with the feature value normalization. So what is our objective? So whatever we have got our imaging features, we will normalize the feature based on different imaging acquisition and reconstruction parameters. So we'll use those values to normalize those features. But problem is that for this we require some proprietary information. Say how things working within the CT machine. I am always mentioning CT because in most of times we deal with the CT scans, because any cancer patient first do for the CT scan. Sometimes they are going for MRI because MRI is much more costlier than the CT. So we prefer first to detect with the CT scan. So for the CT scan acquisition and reconstruction from whatever any manufacturer is, they are what is inside their machine, that is their proprietary. So we do not get any information. So handling of this proprietary information is a critical. Although we are trying to get some information from their manufacturer, but still it is not sufficient and they are not going to release it. So what the other solution is that we can do more experimentation. We can do scanning more 10, 15 or 100 times. So here we have done with the 30 patients. So we can do with this experiment with 500 patients. And now we can statistically find a relationship between these things. So we can try to find out statistically any relationship between how these feature values are changed with this effect, and we can naturally we can go for the feature normalization. So a feature normalization is very essential to remove the variation of the image acquisition or reconstruction parameter, or either you have to do feature normalization or we have to make our feature robust enough so that they are not varying over any kind of imaging setup. Because these two things, because feature reproducibility is very much essential to sell your feature or your any CAD tool based on your own developed feature in market. Because you don't also, you cannot fix it that okay, my system will only work with the G machine, then your market value will be decreased. You will get less customers because your any radiology center may purchase a CT machine from G, Philips or any other company. So we cannot fix. We can, or what we can, so if we fix that okay, my method is only working with the G machine or Siemens machine, then we'll get less market for our product. Now this is our team of collaborators. This is the principal investigators, and all these people are researchers. Some are engineers, some are MD, some of them are doctors, some of them are statisticians. We have a huge group of researchers. Then these people are the surgeon. These people are the pathologist. These people are the medical oncologist. These people are the radiologist. They are the data analytics, and he is working on digital pathology. So these are our faculties, and these are our researcher teams, and he is our principal investigator. And beyond this, we have a set of research staff. They are our research staff, those who helped us in coordinating between us. We have a very large research team, so they helped us to coordinating within department, data collection, or all. We have many formalities in here to collecting in, as we are handling with the medical data, which is very sensitive. So they are helping in that managing all those things. And these are, I must acknowledge our funding agencies and different partners who helped us in different ways. Somebody helped us monetarily, somebody helped us by providing their CT scans, somebody provided us with some, say, G Global Research had given some information about the same machine. So without all of their help, NIH and AAC are mostly funded our researches. So without their help, we cannot do this research. So I must acknowledge this entire team as well as entire of the funding agency as well as the research collaborators for this research. So I conclude here. I have 15 minutes time. So if you have any question, you can ask me.
Okay, Abhishek, I will share my screen now. There are some questions that you can read on the screen that I will share, and you can try to answer those questions.
Okay, thank you, Rajiv.
Can you see, Abhishek?
Yes, Nilesh Nishant. What is the threshold value of accuracy we can reach at the conclusion at particular image that considered for the diagnosis purpose? Mm, Actually, generally, our goal is always 100%, but it is not always the accuracy. In medical term, when we try to sell a product or develop a CAD tool, based on our application, we don't only rely on the accuracy, there are some other parameters. Accuracy doesn't give you the entire clear picture, so we use sensitivity, specificity, as well as positive predictive value and negative predictive value. And based on the use, we try to get which one we want to maximize.
Okay. Now, the
So,
next question is somebody explained this answer about the
okay.
statistical. Okay. Now, next question is Rahul Sharma. How to handle 3D volume scans such as MRI?
Frankly speaking, I didn't work with the MRI, but what I have done in the CT scans, we all of our method is on 2D slice based, and then we take the, say you extract one feature for all the slices, say, and you take the median value, because for the both end of some organs are very small size becomes, so it may be erroneous, so you can do averaging, but I prefer to do extract features over all slices and then take the median value.
Okay. So we go to the next question by Ankit Kandpal. With the techniques like Fourier slice theorem and Radon transform, which guarantees complete reproducible of image, why is CCC important in CT images?
I didn't study these things because Fourier slice theorem I do not know, frankly speaking, or Radon transform, which guarantee complete reproducible image from what I didn't get the question actually. And because CCC is important in CT images, because in my understanding, what I have observed, that if you have vary this parameter, if two images becomes different, then always most of the texture imaging features become, for many times the imaging features become non-reproducible. And another thing is that when you many of the features, sometimes some when you try to, so which technologies actually, frankly, I didn't get the question first of all, and then I don't know that how Fourier slice theorem, I don't know Fourier slice theorem, and I know Radon transform, but I don't know what is Fourier slice theorem and how these produce reproducibility image, I do not know. So I will check, and you can and contact me offline. I will try to find out the answer. But in my observation, what I have seen, that with the variation of the parameters, the imaging features value changes naturally. That's why we try to find out the features which are having CCC value.
Next question is A. Majumdar.
Acquisition and reconstruction parameters signal image quality. Controlling of these parameters, workmanship. What is the advantage of the normalization? Okay, if we want to, if we can do the a very good algorithm for the normal feature normalization, then what will happen? It will eliminate the effect of all these parameters. So all of your scans will be on same level, not the scans, but at least the feature extracted. Say you have an image where ASR value is 20% and you extracted a feature, and I have an image where ASR value is 40% and I have extracted the same feature from that image. Now our feature value has some difference. So what we can do with this normalization, with the information, say if we can build some normalization method with these values, those two feature values will be the same. So it will be easy for to development of a robust computer-aided detection or diagnosis.
Okay. Next question is from Bashu Bhattacharjee.
I have already explained twice. Should we
Okay. Okay. And again, from the same person, number of features exactly, actually, what does it mean? He is
Okay.
trying to ask.
Okay. So number of feature means in our current all these experimentation, we have extracted different well-known imaging features. So what is GLCM? GLCM means gray level Quokkan's matrix. From GLCM, we can extract up to 19 features. So we have extracted 19 features from GLCM. Again, from ACM1 is the angle Quokkan's matrix. These are basically transformation and image to based on their spatial intensity properties. So from ACM1, we again extracted 19 features. Again, from ACM2 matrix, we have extracted 19 features. And now all together, we have 254 or 255 features. And for the pancreas, radiologists have invented use some shape or margin features. So for that project, we have something around 264 features.
Okay, next
And
question.
if you go through any of our papers, there what are those features, all those things, and appendix was added in the papers. That what are how many number of features and what are those features, and these features original papers link all everything will find.
Okay, so next question is Nilesh Nishant again. You can see if two radiologists have different observations, then how can we understand which one is correct?
Uh, Here in this study, for the pancreas segmentation, their observation is very close. But for the tumor, they are actually they both of them have detected the tumor rightly, but they drawn their outline contour different way. And this thing is always here. In many of the recently, I can give you one example of another of my study. Here, two radiologists who are unaware of the study, I have given some scans to provide their opinion, and there is a method called kappa value by which we measure the agreement between two radiologists. Another when we have a decision making thing, not the two contours. Say and they have to classify these patients either of four type of cancer, and their kappa value was standing sometimes 0.75. So I can show there are many examples. Two radiologists, when they are giving these images differently, their observation in the even in the world's one of the best cancer center, their opinion differs. But here, what happens after this? When they go for regular routine clinical practice, after reviewing by one person, a case is generally reviewed by another radiologist, and then these two persons sit together. They individually give their opinion. They have a opinion, and they have a debate, and then based on the debate, they have taken a decision. And sometimes more number of patients, because I know in our hospital there is a weekly 1 day is available. On that day, all radiologist or surgeon they sit together, and when some radiologist have a doubt or surgeon have a doubt what should do, they sit together, and with and that meeting all other radiologists are present, and they provide their opinion over that, and they
Okay,
make a try to build a consensus.
next
Yes,
question
DICOM is actually
on.
DICOM is a format. DICOM is a format, and DICOM image, if you extract a feature from DICOM images, this is a part of the radiomics. Generally, all images which are from all radiology images, features extracted from the radiology images are radiomics. And if you extract these features from the pathology images, we call them as pathology.
Okay. Next is what does the curve graphs B in liver and pancreas tumor signify?
Okay, curve B is basically another representation of the curve E, which is so it just gives you the which features, how many it basically gives you just one. how many features. Here we just getting in the curve A, where we saw some bar plot. They are basically for the pancreas tumor. They are basically we give the number of feature with the hard threshold of more than 0.859, number of feature more than 0.85, and number of feature more than 0.8. But from the curve B, you can visualize. If you want to see how many features more than 0.2, this thing also you can visualize. Say if you see here 0.2, take a vertical line, and all these features outside right hand side of the 0.2 are the features which are reproducible more than 0.2. Can you get my answer?
Yes,
So
yes.
if you
Next,
draw
next is the last question. How
uh,
much exposure of radiation is safe for the patients? What kind of filters are used in the scanners?
this thing I really do not know, but I have heard that within the scanning room the radiation range is very high. Sometime I forgot about these things, but
Okay.
I do not know because I am not a radiation expert or radiology person, so I do not
No
exactly
issues.
know how much amount of radiation was there.
Okay. So we come to an end of our second session today, and thank you all the participants for your presence, and Abhishek, thank you very much for such a nice explanation. We will share the feedback of the participants with you. Very nice feedback we have received, and around 400 participants were there listening to you from different parts of this country, as well as maybe some from outside India also. So thank you very much once again from the organizers, and from on behalf of NIT Silchar. Really, we miss your company. Uh, it was nice when we were together, fine. But yes, of course, it was a very good presentation altogether. And stay safe, stay healthy during this time of pandemic.
Thank,
Thank you. Thank you very
thank
much.
you, Raditya. You also be stay safe.
Yeah. Thank you. Thank you. So it may be a very early morning in your place. So you took
Yes,
lot of
yes.
lot of time to be here at so early in the morning. So
It is
anyway,
around now. It is 6:30 a.m. So we started around 5 a.m. in the morning.
5
Now
a.m.
just
in the
6.
morning. Yeah, I can understand. So thank you very much. We greatly acknowledge your support for this workshop. Thanks you. Thank you. Thank
Thank
you,
you,
all the
Raditya.
participants. Yes, thank you. Bye bye.
Bye.
Yeah.